Today's topic is going to be the general expression of kinetic energy. So in the last class, while deriving the Lagrange equation, we expressed the kinetic energy in terms of the Cartesian components of the velocity. Today, our task is going to be expressing the kinetic energy in the generalized coordinate form. So we are going to express our kinetic energy in the form of generalized coordinates. So let's start with it. So from the last class, we remember having kinetic energy of the form P, which is the summation I half mi r I vector dot square, velocity square, and I can write it as in this form just to make sure I understand that it's a velocity. So what can I do? Today our goal is to express in generalized coordinates. So that's the goal for today's lecture. This is our goal. Alright, so if you recall from our earlier discussion, r vector I is represented Ri is a function of the generalized coordinate as well as the time, where Qj here represents all the components of generalized coordinates ranging from Q1 to Q small n, right? So what can I do is, now I can construct a differential equation of velocity, okay, dr vector I upon dt, and we have done this plenty of times before, so I'm just going to go ahead rather than explaining it. Summation over j, okay, this is dow by dow g r vector I dot q dot j plus dow. I did nothing but just use a product rule. Now this is my r dot, this is velocity, summation of j, and I get this following equation. I'm just writing the same equation again. So I upon I hope it's not too much. Okay. So in order to get, so let me mark this equation. Alright. Let me mark this equation, and it's kind of an important equation for us. So I've named this equation. Let's call this equation as 1 and this equation as 2. Okay, so in order to get the kinetic energy, we need to square the above equation. We got the velocity in terms of generalized coordinates, see, as well as time, because our coordinates are function of generalized coordinates as well as time. So I'm going to square it. I got velocity. If I square it, I can substitute this in the kinetic energy expression. So let's do that. So in order to get the kinetic energy, we need to square the above equation. What will happen if I square? I have to think. This will lead me to the three conditions, as to say, it will lead me to the three particular expression. One, the first, like one term will involving square of the velocity, and the other term would involve just the linear velocity, like just linear velocity, where the velocity would be linear in that expression, and the other term would be independent of velocity. So I will get three expressions just by squaring this, which can be categorized into three following categories. I mean, I'll get one expression, but the three terms are part of it. It will contain three parts. First part would be involving the square of the velocity. Second part would involve just the first power, which is linear in velocity. Another would be the independent of velocity. So just by squaring, and before going ahead, even in quantum mechanics this is true. You cannot, if I square something, say a plus b square, we know that it's a square plus b square plus 2ab, but in many cases, like, we are not sure about that particular variable as such. So I know this is a weird example, but I don't know why I'm using it, but this is the only way I'm seeing that I can explain you guys. So here it is. So quantum mechanically, what we can do is, let's say we have psi 1 plus psi 2 the whole square. We get psi 1 plus psi 1 plus psi 2. Now here we will have psi 1 psi 2. Following expression would be involve psi 2 psi 1. So this is my a square, this is my b square, and this is my 2ab term, but it is not in the form of 2ab. I mean, AB is not equal to BA in case of quantum mechanics. Similarly, I'm not sure what my variable is. So what I'm going to do is, I'm going to take a different variable. Different variable means I'm going to take the different indices for that particular variable. So I'll write the expression and you'll understand it. So my r square expression, r square expression would be sum of j k dou r I upon dou q j, which is normal. Secondly, I will just name a different index for this particular q, because I have already taken qj. I cannot take qj again because I don't know what the particular variable, what the form of particular variable that will involve in this state of the system. So I'll take dou q j k. So I will have q dot j and I'll have q dot k. So now I'll take 2. As I told you that I gave you a weird example, but I haven't gave you this example so that I'm going to violate over here. No, I just gave an example that to show you that it is not always a plus b whole square is not always a square plus b square plus 2ab. Similarly, I just taken a different index of the generalized coordinate, so it doesn't matter. It's a dummy variable. It's a dummy index, so it doesn't matter. Similarly, I'll get 2 summation over j dou r I upon dou qj dou r on dou t, because and I'll have just only q dot j term. Similarly, my last expression would be dou r I upon dou t the whole square. So this is my squared expression of velocity. So what I'm going to do is, I'm going to mark this equation as 3. I'm going to substitute equation 3 in 1. So equation 1 is, this is equation 1, and I'm going to substitute this equation over here. It might look nasty to you, but it really isn't. So yeah, I've done nothing here, just squared it, and I just gave a different variable indices for each of them rather than putting a square on it. That's it. So my kinetic energy expression would take the following form: half I j k mi dou ri upon dou qj I dou qk j k plus I j. Because why I j k? Because I have I term, I have j term, I have k term. So the summation runs from I, j, k respectively. Now the second case, I won't have half because I had 2, so half and 2 gets cancelled. So I will have an expression which doesn't involve half. My mass will remain intact and I'll get an expression just to, so this would be written here. Now to j I q dot j is q dot j plus half summation over just mi, and which is dou ri on dou t square. Now you can see as the power is reducing, the dependency over j I j k is also reducing, which isn't kind of a surprising element, but it is one of the worthy enough feature to be noted. So what I do is I define a quantity for each of them, because I don't want to keep writing this over and over again. So I say I define a jk which involves half mi is mi dou ri upon dou qj dot dou ri on dou qk, right? Similarly I define bj, which is summation over I mi dou ri dou qj dou ri on dou t, and I define this entire quantity to be c because it's anyway independent of velocity. Dou t the whole square. Oh, that's exhausting. So what I'll do is now I'll define an element. Now I'm going to write so whatever we have indicated like a j, k, b, j and c, I'm going to substitute in this equation so that I will have a worthy enough equation which is not lengthy, but it will speak to me as if the whole information is encoded in that particular equation. jk, I've done nothing, I'm just substituting it, so you can check the mathematics. aj bj q dot j q dot j plus c. So what I'm going to do is, again this looks ugly to me, so I'll redefine this in terms of t. This is my t2, this is my t1 and this is my t0. 2 indicates that it is quadratic. 1 indicates it has power 1 which is linear. 0 indicates that it is independent. Thus, I will write explicitly, my kinetic energy, like Lagrangian, depends upon q, generalized coordinate, q dot, generalized velocity, as well as it depends upon time. So I'm going to write this. T2 is my first element, which also depends upon the following variables, followed by T1, which also depends upon the following variables. But my T0 is constant, so my T0 will depend only on generalized velocity and the time. It will not depend upon the generalized coordinates and not generalized velocity. It will not depend upon generalized velocity. So this is my final expression for kinetic energy in terms of generalized coordinates. Of course, I can go more. So in order to solve this equation, you need a constraint condition, say for Celer-Nobis condition. So So let me say the point that, please note this point. I've given notes also. So it's worth noting. See, the transformation equation if it does not contain the time explicitly, that the constraints are time independent, which is a Celan-Thomas condition, then only my T2 is non-vanishing, and my T is always a homogeneous quadratic form in a generalized velocities. Alright, so that's a very important statement to note, because we are going to use this statement in the next lecture also. So an example is in order, which will be helpful for you. Consider a particle this is x, so this is y, this is x, and it makes an angle theta, and it is at a distance r vector, say r from the origin, and the point, and the location of the point is j. So my kinetic energy is given by, in Cartesian coordinates, is given by t is equal to half m x dot square plus y dot square. So my question is, what is my kinetic energy in polar coordinates? In plane polar coordinates, please notice this, plane polar coordinates. Okay, what can I do? I know how to change, transcend from the Cartesian coordinates to polar coordinates by writing this following form: y is equal to r sine theta. So my expression needs the first order time differentiation. So I will do x dot r dot. So I'm just using the product rule, nothing more, r sine theta, and I will have a theta dot component as well. Theta depends on time. And y dot will be r dot. Now times will be sine theta, and minus become plus, and we will have r cos theta. Yeah, we will have r cos theta, theta dot. R cos theta, theta dot. So I'll substitute this by squaring this. I'll substitute this by squaring this. I will have an expression something like this of m, and after solving this you will find the equation of motion for this particular case of kinetic energy will be of this form. Please note this expression. I'm going to use this in the next topic also. Note this expression, and also the point to it, as I said. That's very important. So this is an example. This will show you how to go from the Cartesian coordinates to plane polar coordinates just by using this form. I know this was just to show you the power of transformation. We haven't used the generalized coordinates yet, but it won't be useful as of now unless we touch the energy conservation topic. So let's see you next video, hopefully.